let us see first one, Hopkinson test using including field winding method. Okay, so here as you can see that this is the circuit diagram for the Hopkinson test, where you are given with two machines. One machine it is acting as a motor, this is acting as a motor, and other machine it is acting as a generator. And how they are connected? They are connected using parallel fashion. They are connected parallelly. First machine it is acting as a motor, second machine it is acting as a generator, and both are mechanically coupled with each other. Both are mechanically coupled with each other. Fine. And now input to this motor it is taken from the power supply. Input to the motor it is taken from the supply voltage, which is DC, and output of the motor it is acting as an input to the generator. And whereas output of the generator is electrical, the same output of the generator it is fed back once again to the motor. Yes, it is fed back once again to the motor. For that sake, this we call it as back-to-back test. Hopkinson test, we call it as back-to-back test. Is it clear, all of you?
Yes, sir.
Here you are given with two machines. You are given with two machines, one acting as a motor, another acting as a generator. For the motor, input is taken from the power supply, which is electrical, and output of the motor, which is mechanical. That motor output it is acting as an input to the generator. And once again, the output of the generator, which is electrical, it is fed back once again to the motor. So here, whatever power we are generating from the generator, it is not wasted. In turn, the output of the generator, it is acting as an input to the generator. We call this Hopkinson test as back-to-back test or regenerative test. Is it clear? And here, yeah, both the motor and generator, they are coupled mechanically using parallel fashion, and in between that you are going to have one switch across which you will find the voltmeter. So the purpose of this is just to check the polarity, whether motor voltage and generator, yeah, motor input voltage and generator output voltage, whether they are having same polarity. Only then we should close the switch. If not, then double voltage it may be flowing in this loop, and which may cause the damage to the motor generator set. For that sake, just to check the same polarity of the voltage, here we are checking with the help of voltmeter, which is connected across the switch. Once voltage is same, only then we should close the switch. Initially, this switch, yes, should be kept open. Now let us see Hopkinson test, including field winding method. Including field winding method means here field winding it is connected in this fashion. Field winding of the motor. Okay, so this is field winding of the motor, and this is the field winding of the generator. So input to the generator is what here? I1 plus I2 minus I4, because I1 plus I2 is the current that is entering from this point, and here you can see that I4 is the current which is leaving the field winding. So input to the motor is I1 plus I2 minus I4, whereas I4 is the field winding current of the motor, I3 is the field winding current of the generator, then I2 plus I3. So I2 minus I3, it is the that okay, sorry, only I2 itself is the output of the generator. Okay, now let us see the description here. This test is called regenerative test or back-to-back test. Why it is called regenerative here? Because the reason for calling regenerative is generator's output it is fed back once again as an input to the motor, because generator output is electrical, whose electrical output it is given as an input to the motor, which is electrical input to the motor. For that sake, this method we call it as regenerative test. Why? Because here we are not wasting any power. All that power that is taken from the generator, it is given as an input to the motor. The other name for calling this as back-to-back test is whatever output we are getting from the generator, it is acting as input to the motor. Further output of the motor, it is acting as an input to the generator. Because of this, we call this method as back-to-back test or regenerative test, which can be carried out on two identical DC machines mechanically coupled to each other. So the condition for this here is that whatever the machines here we are using, they should be identical. Identical in the sense both should be of the same rating. Both should be of the same rating, and they are mechanically coupled with each other with the help of one shaft here. Okay. Thus, the full load test can be carried out on two identical shunt machines without wasting their outputs. So here we are going to test both what is that, shunt machines, one acting as a motor, another acting as a generator without wasting any power. One of the machine is made to act as a motor while the other act as a generator. So here this is going to act as a motor and this machine it is acting as a generator. Okay. The mechanical output obtained from the motor drives the generator. So here in this case, mechanical output of the motor, mechanical output of the motor, it is acting as an input to the generator, and generator output, which is electrical, it is acting as an input to the motor. That is what I have told you in the earlier. Mechanical output obtained from the motor drives the generator, whose electrical output supplies the greater part of the input to the motor. Okay. Then the motor is connected to the supply means only to compensate for losses, since in absence of losses. So here, as I told you, whatever generator output it is there, the same generator it is going to act as a generator output. It is acting as an input to the motor. But see that some extra power supply that is that we are taking the power supply, extra power supply from the DC supply source. Why? Because whatever power we are getting from the sub, generator, it is not sufficient to meet out the losses. So whatever the generated power it is there, all that power it is used to overcome the losses inside the motor generator set. Because of that, here we are taking some extra input power to the motor with the help of DC supply source. With the help of DC supply source, is it clear, all of you? Here, whatever generator output it is there, no doubt it is feeding as an input to the motor, but here that much amount of the output is not sufficient because all that generator output it is used to compensate the losses it only. So for that sake, some extra power you are taking from the input supply, plus minus, that is DC supply. Okay. The motor generator set would have run without any external power supply, but due to losses the motor. Why? Because generator output, whatever you are getting, it is not sufficient because all this power it is wasted just to overcome the losses. For that sake, here we are taking some extra power from the input supply. Okay. Thus, motor takes current from the supply to account for losses. So, motor will draw some extra current to compensate all those losses. Okay. The figure dot one shows connection diagram for the Hopkinson test. So, this is the Hopkinson test circuit diagram. The two shunt machines are connected in parallel. So here how the machines are connected, they are connected in parallel. One of the machine is then started as a motor. Out of these two machines, one machine is acting as a motor, and here the stator connections are not here. This is a some mistake it is there. It is not stator, it is starter. Here it is, here it is starter. Here there is some mistake. This you can write it as starter. Is it clear? Make the correction. This is not stator, this is starter. Okay. Here the starter connections are not shown for simplicity. Means here we are not showing the starter. Why? Because if we show the starter, then circuit becomes complicated. For that sake, here, so whatever the starter connections are there, those starter connections, they are excluded. Is it clear, all of you?
Yes, sir.
Then now let us see the procedure, how to conduct the test. The switch yes is kept open. So initially, this switch yes should be kept open as I told you. The other machine which is coupled to first will act as load on the first which is acting as a motor. So here in this case, for the motor, generator will act as a load, and for the generator, motor will act as a load. For that sake only here this method is called as back-to-back test. The other machines which is coupled to the first will act as a load on the first which is acting as motor. So here for the generator, motor is the load, and for the motor, generator is the load. So here actual loading condition is present. Okay. Thus second machine will act as a generator. The speed of the motor is adjusted to normal value with the help of field rheostat. So before starting the test, switch S should be kept open and we should run the motor with the rated speed. And to run this motor for the rated speed, we need to set the field current. So field current of the motor you need to adjust by varying the rheostat, which is connected in series with the field, so that speed of the motor can be brought to the rated value. Okay. Then the voltmeter reading is observed. Then after setting the speed, we should see the voltmeter reading. This voltmeter reading we should read. Then let us see. The voltage of the generator is adjusted by its field rheostat so that voltmeter reading is 0. So after setting the speed of the motor to the rated value by varying the field rheostat, we should read the voltage of this voltmeter which is connected across the switch. If it is not 0, then you should adjust the field rheostat of the generator. Now you should adjust the field rheostat of the generator so that this voltmeter reading is 0. So if this voltmeter reading is 0 means, then both the input voltage and the generator output voltage both are having same polarity. Because of that voltage, this voltmeter reads 0 voltage. Only then you can close the switch. Only then you can close the switch in this case. Okay. Now, then the voltmeter reading is observed. The voltage of the generator, generator. The voltage of the generator is adjusted by its field rheostat so that voltmeter reading is 0. So this field rheostat, it is adjusted to bring the voltage of this voltmeter to 0, and the field rheostat of the motor, it is adjusted just to set the speed to the rated value, So this is for bringing the motor speed to the rated value, and this is to bring the voltage of the switch to the 0 value, this field rheostat. So both they are having different functions here. Now, this once the voltage is 0 means, what is the condition? They are having the same polarity. Okay. This will indicate generator voltage is having same magnitude and polarity of that of the supply voltage. So after varying the generator field current, suppose if this voltage of this voltmeter which is connected across the switch, if it is 0, then it shows that magnitude including polarity of the generator voltage and with the output voltage both are having same polarity and magnitude. Then you can close the switch very safely. That is the meaning. Now, switch yes is closed. After satisfying the polarity test condition, then you can close the switch yes. Okay. To conduct the test now. The two machines can be put into any load by adjusting their field rheostat. So now, after closing the switch, now what we should do? We should check the performance of the machine which is acting as a motor and the performance of the generator of the machine which is acting as a generators for different loading conditions. For different loading conditions, we need to adjust the field rheostat of the motor as well as field rheostat of the generator. So now, after adjusting the field rheostat values, they are going to put certain load on the machines so that we can read different values of A1, A2, A3, A4, like that. Here we are going to get different values. Using that, you are going to calculate different losses and efficiency finally. Switch S is closed. The two machines can be put into any load by adjusting their field rheostat. As I told you, by adjusting the field rheostats of motor as well as generator, you can put the machines to any different loading conditions. Okay. The generator current I2 can be adjusted to any value by increasing the excitation of the generator or by reducing the excitation of the motor. So, what is the generator current here? So, this is the generator. What is the current that is coming out of the generator? That is I2. So, this generator current I2, this can be varied to any level. This can be varied to any level. If I want high generator current, means I should increase the excitation. I should increase the field current. If I want less I2 means I should decrease the motor excitation. That is the meaning. We should reduce the motor excitation. Excitation means simply it is field current. Don't get confused. Okay. The various readings shown by the different ammeters are noted down for further calculations. For different values of the field current, it exhibits different loading condition, and during that period of time, we should note down all the meter readings, A1, A2, A4, A3, and input voltage. Okay. Using that only, here we are going to calculate different losses and efficiency. The various readings shown by the different ammeters are noted down for further calculations. The input to the motor is nothing but output of the generator. So, input to this motor, it is nothing but what? Output of the generator plus input that is taken from the supply side, plus minus. Input to this motor is taken from the generator output plus DC supply. Okay. The input to the motor is nothing but output of the what is that? Output of the generator and small power taken from the supply. And small power taken from the supply. Okay. Now, the mechanical output given by the motor after supplying losses will in turn drive the generator. So now, mechanical output of the once you give output of the generator to this motor and some small power from the supply, then motor will start to rotate. By taking the electrical input, motor will give mechanical output, and that mechanical output, it is further acting as a input to the generator, which is going to drive the generator. Yes or no? If motor is rotating, means shaft will be rotating, and that will be acting as an input to the generator, which is nothing but mechanical output of the motor, in turn acting as an input to the generator. That is the meaning. Okay. Input of the motor is nothing but the output of the generator, small power taken from the supply. Then the mechanical output by motor given by motor after supplying losses will in turn drive the generator. So output of the motor, it will drive the generator. That is nothing but back-to-back test. Now, let us see the assumptions. What is this V? V is nothing but the input supplied voltage. So this is nothing but the V, which is nothing but the supply voltage. Then what is I1? I1 is what? Current taken from the power supply. This I1. This current I1 is nothing but the input that is taken from the power supply. Then current I2. What is that? I2 is nothing but current supplied by the generator. So generator, it is going to give us the electrical output, which is nothing but this I2. I2 is the current supplied by the generator. Then I3. I3 is what? Exciting current of generator. So here, current that is flowing through the field winding of this generator, this is nothing but I3, excitation current of the generator. Then similarly, what is I4? I4 is what? Exciting current of the motor. So now this I4, which is nothing but the exciting current of the motor, means what? Current that is flowing through the field winding of the motor. So I1 is the input current, I2 is the generator output current, I3 is the generator excitation current, I4 is the motor excitation current, and V is the input supply voltage. All these are the notations. Now, what is RA? RA is the armature resistance of each machine. So both machines are having same rating, means they are identical. One acting as motor, other acting as generator. So they are having their own resistance RA for this. Similarly, RA for this. Okay. Armature resistance of motor and armature resistance of generator. Then eta. Eta is what? Efficiency of both generator and motor. So eta stands for efficiency of both motor as well as generator. Now let us see the input to the motor. Input to the motor means what? Here input, what is the input to the motor? If this is the motor, input to the motor is what? Current that is entering from this side, which is nothing but power current taken from the supply. And I2 means what? Current that is given by the generator. Can anybody tell me what is the input to the motor now? See the notations here. So
I1
current
plus I2.
I1 plus I2. So if this is the motor, current taken from the supply is I1, current taken from the generator is I2. So input is V. So V into I1 plus I2 is nothing but input to the motor. Input to the motor is nothing but V into I1 plus I2. This is plus. Okay. Then output of the motor. Output of the motor is nothing but what? Eta into input. So usually we know that efficiency eta is equal to what? General formula.
Output by input.
Output by input. Okay, efficiency is given by eta is equal to output by input. So now if we have calculated input means what is input here? V into I1 plus I2. Then what is output? From this expression I can write output is equal to what? Output is equal to product of efficiency into input. Yes or no? Product of eta into input. Is it clear?
Yes, sir.
Yes, sir.
Efficiency eta is equal to output by input means, so from this I can write output is equal to product of efficiency into input, eta into input. Same thing here we are using. Output of the motor is equal to eta into input, into input, where input is nothing but here eta is missing. Here you can write eta into input is V into I1 plus I2. V into I1 plus I2. So this is input of the motor and this is output of the motor. Okay. Then the output of the motor will be given as input to the generator. Yes or no? Whatever output of the motor it is there, which is mechanical, output of the motor which is mechanical, it is acting as an input to what? Generator.
Generator.
Input to the generator. Fine. So now in this case, input to the generator is equal to what is input now? Input. So from the same expression, what you can write? Input is equal to output by efficiency. Yes or no? Or otherwise, input to output of the generator is nothing but input to the generator. So what is my output of the motor here? Output of the motor is equal to eta V into I1 plus I2. So output of the motor is nothing but input to the generator. What is my output of the motor here? Eta V I1 plus I2, which is output of the motor. It will act as an input to the generator, which is once again eta V into I1 plus I2. Eta V into I1 plus I2. So now, if this is the input to the generator, then what is the output of the generator? Output is equal to what? Output is equal to eta into input. Yes or no? Eta into input. So if this is eta, if this is eta, and what is input here? Input is what here? Input is nothing but
Eta V I1 plus
eta. Yes, eta V
Eta
into
V I1 plus I2.
I1 plus I2. So now already one eta is here into eta V I1
Eta.
plus I2. So altogether eta square V I1 plus I2. So this is output of the generator, and input to the generator is nothing but output of the motor, that is nothing but eta V into I1 plus I2. Now this is output of the generator. Output of the generator means what? At this side, what is the output you are getting? Eta square. This is generator. Its output is eta square V into I1 plus I2. Eta square into V into I1 plus I2. So this is the output of the generator now. In one form, this is the formula for output of the generator. Similarly, in other form, what is the output of the generator? Can anybody tell me? This is one form by considering efficiency. If you want to calculate same generator efficiency using the formula, what is the voltage from the generator? Since all are in parallel, what is the voltage? Voltage will be, yes, what is the voltage? Voltage will remain
I.
same in the parallel circuit. What is the voltage here?
V.
V. And what is the current from the generator?
I2. I2.
I2. So V into I2, this is the other form of output of the generator. Similarly, eta square V into I1 plus I2, this is also the other form of output of the generator. So both they are the equations for output of the generator. Now, output of the generator is equal to eta square V into I1 plus I2. Call this as equation number 1. Similarly, output of the generator can also be given as V into I2, like how just now I told you, that is nothing but product of voltage into current given by the generator. Current given by the generator is I2 and voltage is V. So V into I2, this is also output of the generator. Similarly, eta square V into I1 plus I2, this is also the output of the generator itself. Okay. So now V into I2, whatever you are written here, output of the generator, right? Or call this as equation number 2. So both equation 1 and equation 2 represents what? Output of the generator itself. So in that case, I can equate both the equations, yes or no? If both they are the output of the generator, I can equate both these equations. That is eta square V into I1 plus I2 is equal to V into I2. V into I2. Here V is missing. Is it clear, all of you? Now equate both these equations. Now, if you observe both LHS and RHS, so voltage V is constant, is common. So in that case, I can cancel voltage on both the sides, and finally eta square is equal to what? Eta square is equal to ratio of I2 upon I1 plus I2, or efficiency eta is equal to square root of I2 upon I1 plus I2. So what is this I2? Current given by the generator divided by current taken from the power supply, that is I1, plus current given by the generator, that is I2. So this is how we are going to calculate the efficiency of the generator. Right. But here there are certain limitations. What are those limitations? If we use this formula to calculate the efficiency, let us see now. But the assumption of equal efficiency of two machines is uh, true in case of only for large output machines, where difference in armature current of the two machines is not large. Also, difference in excitation current required to circulate full load current in the armature will not affect the iron losses. So actually, the method to calculate the efficiency using this formula eta is equal to square root of I2 upon I1 plus I2. This is true only for the large machines. This is true only for the large machines where difference in armature current of motor and armature current of generator, that difference is not is very small. IA is also difference in the armature current, also difference in the field current, that is excitation current of motor and generator. That difference is not very large in the case of large rating machines. But if you take small rating machines, then there will be large difference in armature current of motor and armature current of generator. Similarly, there is a difference in field current of the excitation current of motor as well as generator. So in that case, this efficiency equation is not going to work out to calculate the efficiency. If that is the case, then separately we should calculate the field copper loss, armature copper loss, input, output, everything, and then finally we should calculate the efficiency. So how to calculate the efficiency if the rating of the machine is small, that we can see now. Okay. But in case of small machines, the difference between armature and field current is large. So efficiencies cannot be assumed to be the same. So if the difference between IA and IF of motor and generator, if they are large, then obviously losses will not be constant. So they will be keeps on changing. And in that case, we cannot say that efficiency of motor is equal to efficiency of the generator. So that assumption will not be true in this case. Okay. Here the stray losses are assumed to be equal, whereas armature and field copper losses are separately determined for estimating the efficiency. So if the rating of the machine is small, then we should calculate separate iron loss, separate armature copper loss, separate field copper loss. But whereas stray losses, they can be assumed equal for both motor as well as generator. So how to calculate that separate armature and field copper loss for the small rating machines? Let us see here. So armature copper loss in generator. So armature copper loss in generator means you should see the input to the generator. So if you see the circuit diagram here, what is the armature section? This is the armature section of the generator. Yes. So if this is the armature section and this is the generator, what is the current direction for the generator armature? It will be outward direction or inward direction? Current will be always outward direction, right? So if you see the direction, it will be outward. And here, if you apply the KCL, what is this current which is coming out of the armature? This current is excitation current, I3. And one more current which is flowing here, this is I2. Yes. So now armature copper loss, it is nothing but I square R. So here I is what? I2 plus I3 square into RA. So this is the armature copper loss of the generator. Is it clear? So armature copper loss in generator is nothing but I2 plus I3 whole square into RA. Similarly, armature copper loss in motor now. In motor, if you take, if this is the motor, so what is the current direction in the motor? Armature current, it will be entering inside the machine. So here, at this point, if you apply the KCL, what is the current now? Here I1 is entering, here I2 is entering. Till here it is I1 plus I2. But here I4 is getting diverted to the field current. So I can say motor armature copper loss is I1 plus I2 minus I4 whole square into RA. Is it clear, all of you? Here motor armature copper loss is I1 plus I2 minus I4. Why minus? Because this I4 is field current, not it is not a armature current, right? So I1 plus I2 minus I4 whole square into RA. This is motor armature copper loss. Is it clear?
Yes, sir.
Yes, sir.
Now field loss in copper loss in field winding to motor. So motor as well as generator. Now you only tell me what will be the field winding copper loss in the motor. If this is the motor, what is the field winding copper loss in the motor? Voltage is V. What is the current?
I4.
I4. So V into I4 is motor field winding copper loss. Similarly, for the generator, what is the generator field winding copper loss? What is the voltage V and what is the current here?
I3.
I3. So V into I3 is the generator field winding copper loss, whereas V into I4 is the motor field winding copper loss. So here there is some correction you should do. So here V into I3, this is not for the motor, this is for the generator. Make this correction. The notes you can make the correction. This is for generator. Copper loss in the field winding of generator, because generator field winding current I3 is what? Because I3 is the generator field winding current. So make that correction. So copper loss in the generator field winding is V into I3, whereas copper loss in the motor is V into I4. Getting my point? Yes. So separately here we have calculated for armature copper loss as well as field winding copper loss. Now total loss. But total loss in generator and motor are equal to the power supplied by the means. So what is the power drawn from the supply? Power drawn from the supply. If you see the circuit diagram, applied voltage is V, input current is I1. So input to the motor is what? V into I1. So from this V into I1, which is nothing but the input power to the motor generator set, if I deduct armature copper loss of the motor, armature copper loss of the generator, field winding copper loss of the motor, and field winding copper loss of the generator, if I deduct all these four losses from the input V and I1, then we are going to get what? Stray losses. Those stray losses, it will be equal for both motor as well as generator. So then suppose if I get some say for example 100 watts as the stray losses, if both stray losses will be equal for both motor and generator, means what I should do, I should divide it equally. If stray loss is 100, if I get, then 50 watts will be for motor, remaining 50 watts will be for generator. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now here, after calculating different armature and field winding copper loss for motor and generator, let us calculate the stray losses now. For the stray losses from the total input V into I1, if I deduct all these four quantities, then we'll be getting stray loss. That is stray loss for both the machines. It is nothing but input. Input is V into I1. V into I1. This is I1 minus armature copper loss of the generator, then armature copper loss of the motor, then field winding copper loss of the generator, then field winding copper loss of the motor. So if you deduct all these four quantities from the input supply V into I1, then you will be getting what? Stray loss of both the machines, that is motor as well as generator. Now if they are same for both the things, then as I told you, we can divide it equally. Assuming that stray losses are equally divided between two machines, stray loss for each machine is equal to WS by 2. If WS is say for example 100 watts, then 50 watts will be for generator and remaining 50 watts will be for motor. So stray loss for each machine is equal to WS by 2. Make it half. Let us calculate the next remaining part. The machine which is acting as a motor. So now the machine which is acting as a motor means first machine. For this machine, let us calculate the total losses. What will be the total losses now? Armature copper loss, which is nothing but what? I1 plus I2 minus I4 whole square into RA plus V into I4 plus WS by 2. So these are the total losses for the motor. Similarly, total losses for the generator will be what? Total losses for the generator will be V into field winding copper loss, that is V into I3 plus what is that? I2 plus I3 whole square into RA plus WS by 2. So that is the generator total losses. So let us see now. The machine which is acting as a motor, total loss is what? Motor armature copper loss, that is I1 plus I2 minus I4 whole square into RA plus field copper loss V into I4 plus stray loss, that is WS by 2. And what is the input to the motor? Input to the motor is, here voltage is missing. Here you should write V. Is it clear? Here only current I1 plus I2 it is there, but along with that voltage V should come. So input to the motor is V into I1 plus I2. Then you calculate efficiency of the motor. Efficiency of the motor is what? Output by input. So for the motor, electrical quantity is input, whereas output is mechanical. So for that sake, we keep what is that? Input as it is, because it is electrical quantity, whereas output which is mechanical, that express that mechanical in terms of input and losses. So output is nothing but what? Input minus losses. So what is the input to the motor? That is V into I1 plus I2 minus losses. So losses of the motor are what? I1 plus I2 minus I4 whole square into RA plus V into I4 plus stray loss whole divided by input. Input is V into I1 plus I2. So this is efficiency of the motor, and the rating of the machine is of small rating size. Similarly, now let us calculate the efficiency of the machine which is acting as a generator. So what is the total losses of the generator? Armature copper loss, that is I1 plus I2 I1 I2 plus I3 whole square into RA plus field winding copper loss, that is V into I3 plus stray loss, that is WS by 2. And output of the generator is what? That is simply V into I2. V into I2. I hope you understood how you have taken that V into I2. See the generator. Generator output current is I2 and input applied voltage is V. So here this V into I2 is nothing but the output generator. Is it clear all of you? So this is output of the generator V into I2. Now finally you calculate the efficiency of the generator eta G, that is equal to output by input. So, output in the case of generator, which is the electrical quantity, the output will be electrical. So keep output as it is, but input is mechanical, expressed in terms of output and losses. So input, we know that it is nothing but output plus total losses. So output is what? If eta G is equal to output is V into I2 divided by input. Input is nothing but output plus total losses. That is, output is what? V into I2 plus total losses is I2 plus I3 whole square into RA, armature copper loss of the generator plus field copper loss of the generator plus stray loss of the generator. So this is how we are going to calculate efficiency of the generator. It is small rating machine. Right? Is it clear all of you?
Yes, sir.
Yes.
The reason behind calculating this method is here efficiencies will not be same if rating of the machines are different or small in size, because if motors or generator, if it is having large rating, then difference in the armature current of motor and generator, similarly difference in the field current of motor and generator, they will be not having much difference, so efficiency will be same for motor and generator. But if they are having small rating, means IA and IF difference will be large. Because of that, efficiency of the motor and efficiency of the generator will not be same, even though they are having similar rating machines. For that sake, if it is having small rating machines, you need to calculate this formula. Okay. Now finally, let us see the advantages and disadvantages of Hopkinson test. The various advantages of Hopkinson test are: first one, power required for conducting the test is small compared to full load powers of the two machines. So here power required is very small. Why? Because output of the generator is acting as an input to the motor. So power taken from the power supply side is very small. Since the machines are operated at full load conditions, change in the iron loss due to distortion in the flux at full load will be included in the calculation. So here, even though you are not connecting any load, but for the motor, generator will be the load, and for the generator, motor will be the load. So here full load conditions are present. Because of that, change in the iron loss, everything it will be included. Because of that, connection, whatever calculations we are doing, we are getting exact values. As the machines are tested under full load condition, temperature rise and the quality of the commutation of the two machines can also be observed. So here, testing is done using full load conditions. So here we can ensure about the temperature, what will be the rise in the temperature, and whether the commutations will be satisfactory or not. All those conditions can be verified very easily. Then, test is economical as power required to conduct the test is very small, which is just enough to meter out the losses. So as I told you in the beginning, is economical. Why? Because it requires very small amount of the power supply. There is no need for arranging any actual load. Similarly, by changing the field currents of the two machines, the load can be easily changed and a load test over complete range of load can be taken. So as I told you here, for the motor, this generator is the load, and for the generator, motor is the load. And how to put the load on this? Just by changing the field current of the generator. Similarly, by changing the field current of the motor. That is, if I change the excitation of the motor, if I change the excitation of the generator, that is going to exhibit different loading conditions for motor and generator set. So this is how you can change the load for motor and generator set, and you can get load condition, loading condition, and different values for which I can estimate the efficiency very easily. So everything is can be conducted very easily in the case of Hopkinson test. So these are the advantages. Now let us see the disadvantages. There is difficulty in availability of two identical machines. So here it requires two different machines. So that is that too there should be of same rating machines. That is the main drawback of the Hopkinson test. There is a difficulty in availability of two identical machines. Same rating, everything, their performance, everything should be same. Such machines we should use it for the Hopkinson test. So getting such machines is difficult task. Then iron losses in both the machines cannot be separated. So separate iron loss in the motor will be different, and my iron loss in the generator will be different. So those losses we cannot separate it. But some we are getting the cumulative value of what is the iron loss of generator and what is the iron loss of the motor, but we cannot separate it here. Iron losses are different in both the machines because of different excitations. So here we are changing the excitation current I3, which is the excitation current of generator, and I4, which is the excitation current of the motor. So if we keep on changing the excitations, then iron loss in motor will be different from iron loss in the generator, and both we cannot separate it. That is a drawback here. Machines are not loaded equally in case of small machines, which may lead to difficulty in analysis. So, if it is large machine, we can load the machine for 100% full load condition. But in the case of small rating machines, here we are not loading the machine for full load value. So that is the drawback if it is having small rating machines. So all these are the disadvantages and these are the advantages. Is it clear, all of you? So in the exam, if they ask anything about with a neat sketch, explain Hopkinson test means you should start to answer from this side. Okay, this theory part, then this circuit diagram, then all this theory, because this is 8 to 10 marks question in the final weighted exam, and all these assumptions, formulas. Then what if it is small rating machine? Then you need to calculate what is that different losses separately, and at the end you will reach to the efficiency of the motor and efficiency of the generator. Finally, you should write advantages and disadvantages. Is it clear? And this method is what is that Hopkinson test, including field winding method. And usually this will be asked for 8 to 10 marks in the final weekly exam. Is it clear? Yes.
Yes, sir.
Yes, sir.
Can you see the screen now? Yes. So in real time, this is the motor generator set. Can any uh, can anybody tell me? Can you see the screen clearly?
No, sir.
No, sir.
The
No,
screen
sir.
is visible to all of you.
No, sir.
No, sir.
No, sir.
No,
Not
sir.
visible.
Yes.
No, sir.
Screen is not visible, sir.
The screen is visible to all of you.
No, sir.
No, sir.
No, sir.
Yes.
You are left, sir.
Can you see the screen, all of you?
No, sir. No, sir. Not visible.
Now can you see the screen?
No, sir.
Now you check, is it visible?
Yes, sir.
Yes. Yes, sir.
In the real time, whenever you are conducting the lab no, for a Hopkinson test, this will be the usual setup for Hopkinson test. Right. There you can see there are two machines. One will be the motor and another will be the generator. Okay. And this is the circuit diagram for in real time how the diagram it is going to look like. Now, in the previous case, we have seen a Hopkinson test including field winding method. Sometimes in the final video exam, they may ask a question related to the need sketch explain Hopkinson test excluding field winding method. And whatever problems you will be finding, and all those problems usually or majorly they will be based on excluding field winding method only. So now let us see what is that Hopkinson test using excluding field winding method. So that is nothing but alternative connections for Hopkinson test. So now in the excluding field winding method, this is the circuit diagram. So excluding field winding method means directly it will be coupled. This field winding of the motor, it will be directly coupled here. But in the earlier case, this field winding of the motor, it is connected to the motor. Just you can make out the difference. This field winding, it is connected to the motor in the earlier case, whereas now this field winding of the motor, it is directly connected across this power supply. If you want, you can note down the circuit diagram for Hopkinson test excluding field winding method. I will give 2 to 3 minutes. Just you can note down the circuit diagram if you want. Or shall I explain? Do you want to note down the circuit diagram? Title for this is Hopkinson test excluding field winding method. So this is a circuit diagram where field winding of the motor and field winding of the generator, they are directly connected here. And motor here, this is the field winding of the motor and this is the field winding of the generator, where it is excluded from the motor and generator set and they are directly connected to the power supply lines. Right, now let us see the calculations part for Hopkinson test if it is having excluding field winding method. So alternative connections for Hopkinson test, figure 3.1.7. So figure 3.1.7 is this is the circuit diagram for Hopkinson test excluding field winding method, which is nothing but figure 31.7. Right, where field winding of the motor and field winding of the generator directly they are connected to the power supply lines and excluded from the motor and excluded from the generator. Now, in figure 31.7 is shown in slightly different method of connecting the two machines to the supply. Here the main difference is that shunt winding are directly connected across the lines. So here field winding of motor and field winding of the generator, they are directly connected to the power supply lines like what I told you just now. Hence the line input current is in I1 excluding the field current. So now here in this case, current taken from the power supply is simply I1, which is not having field current of motor and which is not having field current of the generator. So completely it is excluded from the field current of motor and generator. Okay, the efficiencies can be calculated as below. So now let us calculate the efficiency of the motor and efficiency of the generator separately here. Motor armature copper loss. So now let us calculate what is the motor armature copper loss in this case. If this is the motor, what is the current that is entering into the motor here? Can anybody tell me? What is the armature current? I1 plus I2 whole square into armature resistance of the motor, that is Ra. So I1 plus I2 whole square into Ra is the armature copper loss of the motor. Fine. Then what is the generator armature copper loss? Generator means current direction will be outward. And what is the current that is taken from the generator? I2. So I2 square into RA is the generator output armature copper loss. I1 plus I2 whole square into RA, this is motor armature copper loss, whereas I2 square into RA, this is generator armature copper loss. Then what is the power drawn from the power supply? Power drawn from the power supply is simply input supply voltage V and I1, excluding field currents. Excluding the field currents. Okay. Now let's see the remaining calculations. And let us calculate total stray loss. Total stray loss, that is friction, windage, and iron losses of the two machines are. What is the input here? Input is V into I1 minus of armature copper loss of the motor, that is I1 plus I2 whole square into RA, minus of generator armature copper loss. So that is nothing but I2 square into RA. So if you deduct these two losses from the input supply, then you will be getting stray losses W, say. So stray loss of each machine is W by 2. We are making it half. Now let us calculate motor efficiency. For motor efficiency, let us calculate motor input first. So motor input is what? Armature input plus shunt field input. So armature input is what? V into I1 plus I2. So what is the input to the armature here? You can just see the circuit diagram. Input to the armature is V into I1 plus I2. Yes or no? Supply voltage V and armature current is I1 plus I2. So this is input to the motor. Along with that, you should also consider for what? Shunt field input. What is the field winding input power here? What is the current that is flowing through the motor field winding? I3. And voltage is V. So V into I3 is the field winding input, whereas V into I1 plus I2 is the armature winding input. So this is completely input to the motor. That is completely input to the motor. Then what is the input? That is W into input. That is input to the motor. So altogether V into I1 plus I2 plus V I3 plus W input. So this is the motor input. Then motor losses. Motor losses is what? Armature copper loss plus field copper loss. Then stray losses. Armature copper loss is I1 plus I2 whole square into RA plus field copper loss is V into I3 plus W by 2. So always remember, whatever notations here we are using, the same notations we should follow in the circuit diagram also, because using these notations only we are writing the formulas here. They should not change. Okay, they should be same. Armature copper loss is what here? To the motor, I1 plus I2 whole square into RA. Field copper loss is what? I3. What is that? Field copper loss V into I3. V into I3 plus stray loss W by 2. So this is motor loss, and this is the motor input. Finally, motor efficiency eta M is equal to output by input. So what is the output? For the motor, output is mechanical. So convert in terms of input and losses. That is W input minus losses divided by W input. So W input it is known, and now Wm, keep it as it is, then W input it to 100. So this is the formula to calculate efficiency of the motor for Hopkinson test, excluding the field winding method. Similarly, now generator efficiency, to calculate the what is the generator efficiency excluding field winding method. So generator output. So what is the generator output here? Generator output is voltage V, and what is the current from the generator?
I2.
So V into I2 is nothing but the generator output, and generator losses. Generator losses are armature copper loss, I2 square into RA, I2 square into RA, then field winding copper loss, that is V into I4 plus stray losses, that is I2 square into RA plus V into I4 plus W by 2, that is the stray loss. So this is what generator losses, and this is the generator output. So finally calculate efficiency of the generator. Eta G is equal to output by input. Output is what? V into I2 divided by input. Input means output plus losses. Output is V into I2 plus losses is WG. WG already you have calculated the losses here. This is the WG value. Is it clear, all of you? So if in the exam they ask anything about explain Hopkinson test excluding field winding method, means you should explain by drawing a circuit diagram. Is it clear?
Yes, sir.
And the same merits you can rewrite once again. Merits means advantages. Power required for the test is small. and it can be tested for full load condition. And here we can ensure about temperature rise and perfect commutation. Okay, these are the advantages. The only disadvantage is what here, and also we can come to know about full load condition, due to which iron loss due to flux distortion, everything can be included. So calculations will be more accurate. The only disadvantage is what, availability of the two identical machines is the disadvantage part. So second half, whatever I explained, this is Hopkinson test excluding field winding method, for which this is the circuit diagram. And the first half, that is a Hopkinson test including field winding method. So you should get prepared for both the methods, which are for 8 to 10 marks in the final VT exam.